Hello everyone. Chapter 3 Derivatives, Section 3.4 Velocity and Other Rates of Change. Here's a reminder of what the definition of the derivative looks like. We learned that back in Section 2.4 that this was the average rate of change, but this is also definition of the derivative. They're related. In this section we're going to be doing manufacturing operations, cost of productions, marginal cost of production is going to be defined as the rate of change or the derivative of the cost function. So in example 1, a paint manufacturer determines that the total cost in dollars of producing X gallons of paint per day is this following function. So part A is asking us to find the marginal cost when the production level is 500 gallons per day. So marginal cost means derivative. So C prime of X. So to find C prime of X, we do the derivative of the C of X function. Derivative of 5,000 is 0. Derivative of X is 1. Plus the derivative of 0.001 X squared is 2 times this power rule. And then 2 minus 1. So 0.002 X, and this is our marginal cost function. We want to evaluate this at 500 gallons. So we plug in C prime of 500, 1 plus 0.002 times 500, and that's equal to 2. So C prime of 500 equals 2. Therefore, the cost of producing $501st gallon is approximately $2. $2.00. That's part A. Part B, we're going to use, this is part A, this is part B. We just found part B. The total cost of producing 500 gallons, find the exact cost of producing the 501st. This is an approximation of producing the 501st gallon. Okay. The exact cost of producing the 501st gallon would be the cost it produced 501st minus the cost was to produce the 500 beforehand. So C C cost of producing the 501st, then we go back to the original cost function. It's 5,000 plus 501 plus 0.001 times 501 squared. This is equal to, did the math out already, $5,752.001, so 1/10 of a penny. Cost of producing 500 is equal to 5,000 plus 500 plus 0.001 is 500 squared. Plug this into a calculator, and this is $5,750. And we'll come back over here, 5,000 $752.001 pennies minus $5,750 gives us cost for the 501st gallon to be $2.01 of a penny, which is really close to our approximate cost based on the marginal cost, which is based off of the rate of change. That's example 1. Example 2. A spherical balloon is being inflated. The radius r of the balloon is increasing at a rate of 0.2 centimeters per second when the radius is 5 centimeters. Now that rate of change is probably going to change. That rate is going to change depending on what the radius is. The bigger the balloon gets, the slower it's going to be expanding, because the rubber is getting stretched more on the balloon. It's harder to expand it even further. So that rate varies depending on what the radius is. When the radius is 5 centimeters, this is what the exact rate of change is. At what rate is the volume of the balloon increasing at that instant? So we need to know the volume formula is 4/3 pi r cubed in order to do this problem. Alright, so we are given, what is it that we're given? We're given, we're given dr dt, the rate in which the radius is changing with respect to the amount of time that has changed. And that is 0.2 centimeters per second when r equals 5 centimeters. Okay, what we want is the rate of change of the volume. So we want dV dt. We want to find is dV dt in that exact instant. Okay? In that instant. Okay? Because the volume of the balloon is V equals 4/3 pi r cubed, we can find dV dr, because r is the only variable in here. So dV dr, the derivative with respect to r, dV dr is equal to d 4/3 pi r cubed dr, which is equal to what? Well, this is a power rule. The variable that we have here is raised to the third power. Take that 3, multiply it by the coefficients, and then subtract 1 from the exponent. So 4/3 times 3 is just 4 pi r, 3 minus 1 is 2. So dV dr is 4 pi r squared. We know dr dt. We know dv dr. We're looking for dv dt. That's our end goal. Okay, so if we follow this here, we know dv dr. We just found that. We know dr dt. That was given to us. We know dv dr, we just calculated it. We know dr dt, we were given that. If we multiply these two together, dr's cancel, and we're left with dv dt, which is what we're looking for. Okay, this is a concept that's going to become very important to us in the future. A little farther down the road, this canceling of denominator and numerator, multiplying two different derivatives together to get the derivative that we want, that's something we're going to use. It's a much more advanced concept that we're going to use later on this term. So what do we have here? We really have 4 pi r squared times 0.2. Or 4 pi times 5 squared times 0.2. And when we pull out our calculator and do out that arithmetic, we get 62.83 centimeters per second. And that's how much the volume is changing when the radius is 5 centimeters. Okay, example 3. A body falls freely with this position function. Find the instantaneous velocity of the function t, and how fast is the body falling in feet per second 2 seconds after the release. So instantaneous velocity is the derivative of your position function. So the derivative of position is velocity. That would be defined up here. So derivative of position is velocity. So v of t is equal to s prime of t, which is equal to the derivative of this function. 2 times 1, it's product power rule. 2 times 1/2 is 1. G, t, 2 minus 1 is 1. So just g, t, g being gravity. G, because we're measuring things in feet per second. Gravity is 32 feet per second squared is gravity. Okay. So V T is equal to 32 T feet per second. Okay, and why is it just feet per second now? Because this second squared cancels with this seconds from the time to make it just seconds. And when we plug in t equal to 2 seconds, v of 2 is equal to 32 times 2, or 64 feet per second. Okay, speed is just the absolute value of velocity. Velocity can be positive, it can be negative, depending on if you're going forwards or backwards or up or down, or however you've defined the forward or positive direction to be. Speed is always positive, no matter what the direction is that you're going in. So, example 4, we're going to let our position function be t to the fourth minus 8t squared, be a position function of a particle moving along a line where t is in seconds, s is in feet. Find the instantaneous velocity and the speed. Also find the instantaneous velocity and the speed at t equal to 1, t equal to 2, and t equal to 3, and explain the motion of the particle. So we have our position function. What we need is our velocity function. So v of t is equal to s prime of t, which is the derivative of this function, or 4t cubed minus 16t, power rule, sorry. Speed is just going to be the absolute value of that. Okay, so speed is equal to the absolute value of v of t, or the absolute value of 4t cubed minus 16t. Okay, when t is equal to 1, we want to find v of 1, which is equal to 4 times 1 cubed minus 16 times 1, or negative 12 feet per second, which means the particle's moving in a negative direction, whatever that direction may be. Down or backwards, left, right, whatever you've defined as, or whoever is defining this direction to be negative, that's what direction this particle is moving in. So, which means particle is moving in a negative direction with a speed of absolute value of v of 1, or the positive 12 feet per second. So that's time equal to 1, time equal to 2. So time equal to 2 is v of 2. Oops. v of 2, which is going to be 4 times 2 cubed minus 16 times 2. 2 cubed is 8, times 4 is 32, minus 32, or 0 feet per second. Which means the particle is stopped. Stopped. Its velocity is 0. It is not moving. T equal to 3 seconds. So v of 3 equal to 4 times 3 cubed minus 16 times 3. This is equal to, if I pull up the calculator, 60 feet per second, which means the particle is moving in the positive direction with a speed of absolute value of v of 3, which is still 60 feet per second. There's example 4. Example 5. A car is moving along a line and has a position in feet at a time t in seconds of s equal to 5t squared plus 100. What is the car's velocity at time t? Find s of 0, v of 0, s of 10, v of 10. So we know how far the car has traveled and its speed at 10 seconds. So first thing we need to do is find velocity. So we need to find v of t, which again is equal to s prime of t. Which is equal to 10t now. We want to find s of 0, which is 5 times 0 squared plus 100, or 100 feet. V of 0 is equal to 10 times 0, or 0 feet per second. So this car starts at the 100-foot mark. That's its position. It starts with an initial velocity of 0. It's not moving when the clock starts at 0. S of 10 is equal to 5 times 10 squared plus 100. 10 squared is 100, times 5 is 500, plus another 100, 600 feet. And V of 10 is equal to 10 times 10, or 100 feet per second. Therefore, the car has traveled from 100 feet to 600 feet, so therefore, car has traveled 500 feet, and its speed here equals absolute value of V of 10, which is still 100 feet per second. And speed is 100 feet per second. Okay. Acceleration is the derivative of velocity. So velocity is the derivative of position, acceleration is the derivative of velocity, or the second derivative of position. Example 6. The position of a moving body is given by the equation s equals 160t minus 16t squared, where s is in feet, t is in seconds. Find the body's velocity and acceleration at time t. So V of t is equal to S prime of t, which is equal to 160 minus 32t. And that is measured in feet per second. Feet seconds. That's the first half of our question. The second half is A of t, the acceleration, is the derivative of velocity, v of t, or the same as s double prime of t, the second derivative of position. So the derivative of this function is negative 32 feet per second squared this time. Which tells me that this object is falling because that's gravity. Okay, here are some constants that you want to become familiar with. Near the Earth's surface, things change if you're on the moon, or if you're the farther away you get from the Earth's surface. These constants are no longer constant, they change, but when we're down here on the ground, position is given by this function, which we saw in a problem. Velocity is g times t. V is equal to velocity, s is distance, t is time, g is gravitational constant. If we are measuring things in the English units, feet, seconds, then g is 16, okay, or 32, sorry, half of g. So 32 feet per second squared is gravity. Half of gravity is going to be 16 t squared. Velocity is going to be the derivative of this, which is 32 times t. And continue, if we are measuring things in the metric units, then if we're in centimeters, it's 980 centimeters per second squared. If we're in meters, then it's 9.8 meters per second squared. This is the most common of them. So 32 feet per second squared is the most common in the English units, and 9.8 meters per second squared is the most common in the metric units. Okay, and this graph, or this picture, goes along with the last problem. This was the function that we saw a second ago for position of an object being projected out at a certain distance. This is another picture that we're going to use in a second, where we're launching something up into the air. It reaches a maximum height, and then it comes back down. When it reaches that maximum height, its velocity is 0. Its acceleration is still the same. Acceleration going up, acceleration going down, but the velocity here is 0. It's getting slower, but the acceleration is not changing. At what time is it 256 feet off the ground? It's going to occur at 2 different times, which we're going to see in, I believe, the very next problem. Yes. All right, so example 7. Find the maximum height obtained by the ball thrown straight upward on the ground at s equals 0. So the position at s equals 0 is the ground, with an initial velocity of 96 feet per second. Also find the velocity at which it hits the ground upon its return. We have our position function here. And what do we need to do? So we need to first find the velocity, v of t, which is equal to s prime of t, which is equal to, so this is our position function, and here's my spot here. we are measuring things, and so this is equal to negative 1/2 32. So negative 1/2 times 32 t squared plus 96 feet per second. T, sorry, 96 t from here. So initial velocity times t. Negative 1/2 times 32 is negative 16 t squared plus 96 t. And we want to know, when that hits the ground. We'll find its velocity and when it hits the ground. We'll find the velocity later. Let's find when it hits the ground first. So when it hits the ground is when the height is 0. The position is 0. So S of t equaling 0. S of t equaling 0. That's what we want to find here. And that's going to be equal to the negative 16 t squared plus 96 t. This factors. We factor out the negative 16 t. We are left with t minus 6 on the inside. When is that equal to 0? That's equal when t equals 0, which we already knew because this is being launched from the ground. So t equals 0, s equals 0. So t equals 0 and 6 seconds later, it's going to come back down to the ground. So it starts on the ground at 0 seconds, 6 seconds later, it returns to the ground. 3 seconds, it hits its max height. But we want to know what's its velocity when it hits the ground. V of t is equal to s prime of t, which is equal to derivative of this, negative 32t plus 96. And we want to find v of 6 seconds when it hits the ground. So negative 32 times 6 plus 96 is equal to negative 96, if we do out the math, negative 96 feet per second. So its velocity is negative 96 feet. That makes sense because it's going down. It's 96 feet per second when it's going up, the initial blast or throw, and it's negative 96 feet when it returns to the Earth. Question number 8. This is the question that we're going to use this picture for. A heavy rock is blasted upward with a velocity of 160 feet per second, reaches a height of s after t seconds. How high does the rock go? What is the velocity of the rock when it's 256 feet above the ground on the way up and on the way down? Okay, so we want to know what's its max velocity, its max height. That's when the velocity is equal to 0. So we're going to have to find the v of t function, set it equal to 0. And then we want to know what is the time when the height is 256 feet off the ground. And that's going to happen 2 different times. So part A, first we need to find v of t equal to 0. So how do we find v of t? V of t is equal to s prime of t. Again, s prime of t is equal to negative 32 t plus 160, derivative of s. So that is our v of t function. We want to set that equal to 0. So negative 32t plus 160 equals 0. 32t equals 160. T equals 5 seconds after it's initially blasted into the air. It reaches its max height, whatever that max height is. And we can figure that out by plugging 5 into here. What we want to do is we want to, and we can figure that out. We don't, it doesn't ask. Oh, it does. How high does the rock go? So that's when it hits the max height. So S of 5 equals negative 16 5 squared plus 160 times 5. 5 squared is 25 times negative 16 is negative 400. Plus 5 times 160 is 800. So the max height is 400 feet. S max, I'm going to call it that. The max height that it goes is 400 feet above the ground. Okay, now it's got to go up, it's got to come back down again. We want to know, when is it 256 feet above the ground on the way up, 256 feet above the ground on the way down. So it is 256 feet on the way up and on the way down. Lost my spot here. There it is. So now we want to find T. Find T when S of T equals 256. Okay, I'm going to do that over here. S of T equals negative 16 t squared plus 160 t equal to 256. Let's set this equal to 0. Subtract the 257. I'm going to add the 16t and subtract the 160t. So we have 16t squared minus 160t plus 256 equals 0. This can all be simplified, reduced to 256. This can all be reduced by 16. T squared minus 10t plus 16 equals 0. Again, this factors. Equals 0. This factors into t minus 2, t minus 8. So t equals 2 and 8 seconds, which means, what is the velocity of the rock at 256 feet? So this is the time when the rock is 256 feet on the way up and on the way down. We want to know what's the velocity at those. So we want to find v of 2. V of 2 is going to be negative 32 times 2 plus 160, which is equal to negative 64 plus 160, or 96 feet per second on the way up. And then v of 8, velocity at 8 seconds, negative 32 times 8 plus 160, equals negative 256 plus 160, or negative 96 feet per second on the way down, which again makes sense because its velocity, its speed, is the same at the height at 256 on the way up as it is on 256 on the way down. That's example 8. A couple last problems. Let s of t equal to t cubed minus 6t squared, where t is in seconds, s is in feet. Find the acceleration at t equal to 1 second, t equal to 2 seconds, and t equal to 4 seconds. Again, we want to find acceleration. So acceleration is the second derivative of position. So v a of t is equal to s prime of t, is equal to s double prime of t. Okay, well, s double prime of t is going to be the derivative of s of t. So let's find s of t. S prime of t is equal to 3t squared minus 12t. That's s prime of t. S double prime of t, or a of t, acceleration, 6t minus 12. We want to find a of 1. It's going to be 6 times 1 minus 12, or negative 6 feet per second squared. 1. A of 2 is equal to 6 times 2 minus 12, or 0 feet per second squared. And our last one, A of 4. Is going to be 6 times 4 minus 12, or 12 feet per second squared. Alrighty. Last problem. Position function of a particle moving in a line given by this position function, where s is in feet, t is in seconds. Describe the motion of the particle for times greater than 0. What's happening after the initial time of 0 seconds? So let's find the velocity, v of t. Find out if it's going forwards or backwards. Velocity being negative is going to be backwards, positive is going to be forwards. So v of t is equal to s prime of t, which is equal to 6t squared minus 42t plus 100 plus 60. And what are the critical values of this? Well, as factors. Factor out a 6, we get t squared minus 7t plus 10. And this factors again, 6t minus 2, t minus 5. So we have critical values happening at 2 and at 5. And what's happening at before 2 and after 2, what's happening before 5 and after 5. So let's take a look at some position graphs. What is, here's 2. What is the sign t minus 2? Positive or negative? Well, 4 values, and we'll start here at 0. Go from 0 up to 5, up to 2, up to 5, and then beyond. Between 0 and 2, t of minus 2 has negative values. After 2, between 2 and 5, t minus 2 has positive values. And even after 5, it's going to have positive values. It just continues to have positive values. Okay? What about 0, 2, 5? What about the sine of t minus 5? Between 0 and 5, it's negative. After 5, it's positive. Okay. These are being multiplied together. T minus 2 times t minus 5. Negative times negative, positive. Positive times negative, negative. 0 here and here. Positive times positive, positive. So this is moving in a positive direction. Whatever that is defined as. Then it stops. Then it moves in a negative direction. And then it stops again. And then it moves in a positive direction again. One last time. Okay? Well, that's most of the problem. It's not the complete problem. Because what's it doing between 0 and 2 and between 2 and 5? Okay? So, well, if it's going to be stopping, then it's going to be slowing down. If it's going to be stopping, it's going to be slowing down. And that's going to be speeding up after it stops. It's going to be speeding up after it stops. But at what point does it start slowing down? And at what point does it start speeding back up again? So to do that, we're going to look at A of t. A t, which is equal to v prime of t. So v prime of t is 12t minus 42. And that factors 12t minus 7 over 2. And what's a critical value for this? That's time equal to 7/2 or 3.5 is a critical value. So 0, 2, 1, 2, 3, 4, 5. It's 5, 3, 4. 7/2 or 3.5. It's slowing down before it gets to 2. At 2 it has stopped. It's speeding up. Until it gets to 3.5 or 7/2. And it's slowing down. till it gets to 5, and it stops again, and then it's speeding up again. After 5. It's just going to keep getting faster and faster and faster. All right, that's the end of this unit. You should do the bookwork, and these IXLs are pretty good to look at, to try and practice. And that should be good. Thank you very much. Bye.